day to our lecturer and fellow classmates. Today our group will be representing on our Discrete Mathematics project titled the Password Reset Flow. We'll be exploring the hidden logic behind this common security feature using function, graph theory, and trees. Our team members include Faiqah, Zulaikha, Huda, and myself, Khairiah, Fatnin. Now going on objective. Whenever we forgot our password, we simply click Forgot Password button without realizing there is a complex mathematical structure running behind the background to keep our account always be safe. So, the objective of our project is to model the exact workflow using function, graph theory, and trees based on our four main steps, which is request, email send, token, verify, and the new password. Now, we're going on function model and set mapping. Let's begin with the function model. To define a mathematical function, first we need to establish our set. Here, set X is our domain, which is represent the user who requests a password reset, such as user A, B, and C. Set Y is our codomain, which consists of the unique security tokens generated by the system. As you can see, our mapping diagram, each user is mapped directly on their own specific temporary security token. Next, function model, classification, and inverse. Now, how do we classify this function? This is a strictly one-to-one or injection function. Why? Because in cybersecurity, every single user must receive a complete unit token. If two different users map to do the same token, it will cause a massive security breach. So, let's look at the inverse function. Think of this like a function, a cancel or back button. If a user accidentally requests a reset and hits cancel, the inverse function safely cancels the specific tokens and return the user back to the normal login screen. Now going on function model composition. We also have function composition, represented as this model has a two-step G or F sequence process. Function F is the first step where the user requests a reset and the system sends the token. Function G is the second step where the token is getting verified, allowing the user to create a new password. The composition function G or F combine this step, representing the seamless user experience for the initial click to the final successful password change.
Moving on the graph theory model, we can visualize the entire password reset flow as a structure made of vertices and edge. Our vertices, or we call it nodes, represent the four security state, which is request, email send, token verify, and new password. This graph is direct. The graph means the path is strictly one way. This one way is critical for a security, ensuring that user cannot skip this step. For example, you cannot jump straight from request to the new password without verifying the token first. Next, let's analyze the degree of our vertices. If we look at the token verified node, it has in degree 1 and out degree 1. In the real world, this specific node acts as a critical bottleneck or gatekeeper. Even though it is a simple sequence step, if a user experiences network delay or lets the token expire, the entire flow gets blocked right here, forcing them to restart the process from the beginning. To make our graph computer readable, we represent it using n multiple n adjacency matrix as shown at the slide. A value of 1 indicates a valid directed path from one state to another, while a 0 means no directed connection instance. For example, there is a 1 from request to send email, but a 0 from request to a new password, mathematically proving that the system enforces a strict step-by-step sequence.
Our final module is the tree module, where we use a decision tree to map out the conditional outcomes of the system. The root of our tree is the initial request states. As we move down, the initial nodes represents system checks, such as is the email valid or is the token expired. Finally, the leaf represents our endpoints. Leaf 1 is a successful password reset, while leaf 2 and 3 represent system failures due to an invalid email or an expired token. In conclusion, discrete mathematics is truly the hidden architecture behind digital security. By using injective function, directed graph, and decision trees, software engineers can design authentication flows that are organized, logical, and secure against cyber threats. And that concludes our presentation. We hope this clearly shows the hidden logic of discrete mathematics in our daily digital security. Thank you for your time.